All right, howdy folks. Welcome to the novel applications in sports analytics side of the conference here. I'm Kevin Rader, I'll be your host. I'm, close colleagues with Mark and Scott, so it's good to be able to lead a few things here. We have three speakers. We're gonna start off with an awesome talk on darts. So Rachael Walker is a recent grad from the University of Toronto, getting her bachelor's in industrial engineering and a minor in artificial intelligence engineering. For her undergraduate thesis, she researched the application of stochastic optimization models for sports. Specifically, she examined how Markov models can be used to design fair handicap systems in this game of darts. So Rachael has just started a new role on the data science team at a private equity firm in Toronto called Birch Hill Equity Partners, and she's a big fan of the Leafs. So if any of you out here are Toronto Maple Leafs fans, come on and say hi. So, Rachael.
Oh, this is off balance. Thank you. I'll just hold this.
You can also just sit behind the podium.
Okay. Yeah, maybe that's easier. Okay. Actually, maybe I can also just enunciate. Can everyone hear me? Okay. Sweet. All right. Well, I'm Rachael. Thank you all for coming today. I'm so excited to be here and talk to you about the game of darts and present to you the outputs of my undergraduate research, which I did under the supervision of Craig Fernandez and Timothy Chan at U of T. So today we're going to talk about darts and how we can use Markov decision processes to create handicap systems that make the game more fair and hopefully a bit more fun. So let's just start by talking about darts. Darts played in a wide variety of contexts. You might know it as a recreational pub sport, and everyone's favorite Ted Lasso, or it's also a professional sport played with up to over $500,000 of prize money at the professional level. So for those of you who are not familiar with darts, let's just quickly run through the rules. So darts is played between two players typically, and we're going to talk about 501 darts. So each player starts with a score of 501. And the goal is to get to 0 as quickly as possible. And players can do this by taking turns throwing darts at the board. And depending on where they land, a player will get a certain number of points, which are taken off their score. And players will throw 3 darts at a time, and they'll take turns doing this. To win, you need to check out before your opponent, or finish the game, or get to 0. But it's tricky, because not only do you have to get to 0, but you have to get to a score of exactly 0, so you can't overshoot and get to... Oh, okay. This one? Okay. Sorry. Okay, so you can't, you have to get a score of exactly 0. Wait, I'll try this again. Okay, so you can't get to a score of, say, -1, or because you've overshot. So you have to get to exactly 0, and you have to hit a double. And doubles are on this ring on the outside of the board, so it's really easy to miss. And what's more is they're each worth an even number of points, or twice the number of points on the outside. So if you have an odd number of points, you actually can't finish the game on your next throw. You have to first move to an even score, then you have to check out. So there's a lot of complexity here. And what's worse is you can go bust. So if you land on a state or on a score where it's impossible to check out, so a score of 1 or a score of like -2, you go bust, and your score reverts to what it was at the start of your turn. And this is challenging, because if you go bust on the 3rd throw of your turn, whatever points you gained in those first 2 throws are discarded. And if you go bust on the 1st throw, you don't even get to make your next 2 throws. So as you can see, there's a lot of challenge in finishing the game of darts. So this is where handicap systems come in. So in darts, you get a really wide range of skill levels. It's an awesome game because it's so easy to play. You just have to throw something at the dartboard, but it's really difficult to play well. And so you might get a novice, like a weaker player, up against a seasoned expert. And this can be kind of boring because if the better player is winning every time and the weaker players losing every time. It's kind of demoralizing for the weaker player and boring for the stronger player. So this is where handicap systems come in. The point of a handicap, as you might know from golf, is to give the weaker player the needed advantage to be competitive with the stronger player and have a fighting chance of winning. In darts, there are handicaps that are used, and they basically operate by giving the weaker player a head start. So instead of starting at a score of 501, maybe they start at a score of 401. But these head starts have never been kind of analyzed before, and there's no guarantee that they actually make things fair. And this is where our research comes in. First of all, we want to develop an optimization-based framework for modeling, understanding, and evaluating handicaps in darts. We want to build intuition around fairness in darts during the process. And we want to go beyond historical handicaps and try something new called a dynamic credit handicap. And this was inspired by Chan and Singel's 2016 paper that does something similar in tennis. Basically, how this works is the weaker player is given a certain number of credits, which is basically a perfect accuracy throw. So if I cash in one of my credits, I can say I'm going to hit the bullseye, and I will get that hit with a probability of 1. And they're dynamic because you can use them at any point in the game. And ultimately, our goal is to propose a handicap system that mathematically balances competition. OK, so now that we've set our aspiration, let's jump into our modeling. For ease of presentation, I'm going to present a slightly simplified model that assumes that there's 1 throw per turn. But later in the results, we'll actually present the results for a more accurate model that considers 3 throws per turn. OK, so we use something called the Markov decision process, or an MDP. Some of you might be really familiar with this, and some of you may have never heard about this, so we'll walk through step by step. What's awesome about MDPs is it's a really nice way to model an agent, in our case a player, in their environment. And so we do this by first acknowledging that a player is in some state, which we'll call S. In our case, our states consist of the player's remaining score from 0 to 501, and a player's remaining credits from 0 to 9. Now, you might wonder, why 0 to 9? 9 seems like a random number. This is because the perfect game of darts is called a 9-dart finish. It's impossible to get from 501 to 0 in less than 9 throws. And likewise, if you have 9 perfect accuracy throws, you're never going to need more. So adding 10 credits would just be kind of redundant. OK, now we know where a player is in the game. We want to figure out what's the best action that they should take in that state. For our actions, there's sort of 2 subsets that a player can choose from. Either they can throw, or they can use a credit. For throws, we picked 729 targets that a player can choose between. And for credits, there's 62 possible board regions that a player can choose from and hit with perfect accuracy. So we talked about these doubles around the outside worth 2 times the amount of points. There's this triple ring on the middle, which is worth 3 times the amount of points on the outside. And the rest of the pizza slices are kind of, they're single, so they're worth exactly the amount of points on the outside. And then there's a single and double bullseye in the middle, so 62 regions. OK, a player's chosen an action, and now there's uncertainty. This is where the environment comes in. And we model this with transition probabilities. So what is the probability that a player will end up in the next state S prime, given that they're in the current state and they chose a certain action A? So these probabilities are action dependent. And so if a player chooses to throw, there's going to be some uncertain outcome because they could miss. And so in order to model this uncertain outcome, we piggyback off of Howe and Wing's 2022 paper called Play Like the Pros. Great paper. It also looks at darts. And what they did was they took 16 professional players. They looked at the throw outcomes for known targets, and they fit bivariate Gaussian distributions, which is basically just a 2-dimensional normal distribution for those of you who are not statisticians. So if you have a dartboard and they're aiming for the middle, we get some sort of density of where the dart will land, given they're aiming somewhere. And if they use a credit, it's pretty nice because it's a deterministic outcome. They're going to hit that desired board region with certainty. OK, so now that we have these transition dynamics, we can return some outcome. We move to our next state, S prime. And every action is given a cost of 1. And that helps us determine the value of each state, which we'll get back to in a minute. OK, one thing that's missing from this modeling framework so far, though, is skill levels. We need to model stronger and weaker players. And so where does that come in? So we do this by introducing something called an execution error multiplier epsilon. And this was taken by Chan and Fernandez's 2022 paper, again, looking at something similar in tennis. And essentially how this works is we start with our pro, and we take their distribution, and we model this spectrum of weaker players by adding this scalar multiple to the covariance matrix. So if we have a pro aiming for the bullseye, we'll expect it to be pretty tightly distributed around their target, whereas for a weaker player, it'll be more spread out. OK, so back to our MDP. We have this model that we've defined, and we plug this now into something called the Bellman equation. We won't jump into it too much, but it basically consolidates everything that we've qualitatively talked about. And when you solve this, you get 2 important things. First of all, you get an optimal policy, which tells you for this player, what's the best action I can take at any state of the game. And we get an optimal value. The optimal value might be a little less clear within all this math, but we can actually prove a few things about it, which will be helpful for the rest of our conversation. So first of all, we can prove that our value function corresponds to the expected number of throws to finish the game when using a given policy. And this is really nice because it can allow us to define 2 other important concepts for our work. First, we can say that weaker players are the ones that take more throws to check out on average when starting from a score of 501 with no credits. And we can define competitive balance as occurring when 2 players take an equal number of expected throws on average. And so for those of you who are statisticians out there, you might note that this is a somewhat naive definition because aligning how long it takes, the expectation for the number of throws to check out, doesn't necessarily mean 2 players will win the same amount on average. You have to consider the full distribution, but this is readily accessible within our modeling framework, so we're going to run with this definition for a little while. And then finally, one other thing that's good to note is we can prove that there will always be a number of credits that gives the weaker player the needed advantage to check out with equal or less than expected throws compared to the stronger player. So that's just a good preliminary benefit of our handicap system. OK, enough modeling. Let's actually jump into the results. Like I mentioned earlier, this will actually look at the full game of darts that considers this whole going bust with 3 throws in a turn. OK, so let's start by solving without credits. Let's just look at the base game of darts and build some intuition. We're going to do this for 9 players from epsilon 1, which is like a pro level of skill, to our weakest player, who will give an epsilon of 9. OK, so on the top here, we have the skill model. So these are the bivariate Gaussian distributions distributed around a target of the bullseye. So again, we see our pro, everything's really tightly distributed. And for our epsilon 9, there's a little bit less accuracy. And on the bottom here, we actually look at the optimal policy across all states for these 2 players. And this is pretty intuitive, but still kind of cool to see. For the pro, they're shooting for a triple 20, which is the highest scoring segment of the board worth 60 points. And they're shooting for that for most of the game to try to get to 0 as fast as possible. But for epsilon 9, you're actually shooting for the triple 19, which is worth 3 less points if you hit it. But because they're a lot more likely to miss, they actually care about their neighbors. So they care about 7 and 3, which is better than 5 and 1 around the triple 20. So this is sort of neat to see in practice how as players' skill levels change, the optimal way of playing the game also changes. Okay, now that we've talked about policy, let's look at the value function. So on the y-axis here is our value function, the expected number of turns to check out. And on the x-axis is the score. So over here is the end of the game, or the beginning of the game, when players have a score of 501. And over here is the end of the game, where players have a score of 0. And so 2 really obvious things from this graph. First of all, as you get closer to 0, the expected time to check out decreases on average. So that's a good finding. And then as epsilon increases, as a player's execution error increases, the time to check out also increases. But there's a few things that are less intuitive from this graph. So first of all, what's all this oscillation at the end? Why is it all spiky? Well, this comes from the need to hit a double. As soon as you move from an even score to the adjacent odd score, you immediately need one more throw to check out. Also, why does it curve upwards towards the end? Well, this is because of that bust condition. As you get closer and closer to 0, there's less things you can hit without going bust. And so especially for players with a higher level of execution error, they can get stuck in this cycle where they're just unable to check out. So we see that there's this really strong source of imbalance at the end of the game. We also note from this graph that it's possible that the stronger player could actually dominate across all game states. And so, for example, let's draw a line. So this is the amount of time it takes a pro to check out from a score of 501. Imagine a player now with epsilon 15. Their line will never intersect. So no head start would ever be able to actually balance competition. So that's pretty interesting. And with this in mind, let's actually look at these heuristic head starts that are used in practice and see how they do. So these markers represent a heuristic handicap called the spot point, so basically for a player with epsilon 9, they'll start with a score just below 200 using this heuristic system. And as you can see, the time to check out, it's not balanced. It's not along the line. So we know that these handicaps are not achieving competitive balance. But using our framework, we actually can find the optimal head start, or we can find the head start that does equalize competitive balance as we've defined it. And we do this by finding the values where the weaker player's functions actually intersect that of the stronger player. Now, all of this is still within the context of our MDP, but we want to actually see how this performs in practice. And to do this, we need to put it to the test with simulation. So what we do is we solve the MDPs for each player. We take their optimal policy, and we're going to assume that every player is playing optimally for their skill level. We simulate 10,000 matches, and we alternate the starter, because there is a starter's advantage in darts. And then we use the match outcomes to approximate win probabilities. And what we find is that even with our optimized head start handicaps, win probability is not actually equal. And we're actually favoring the weaker player here. So on the y-axis, we have the stronger player's epsilon. And on the x-axis, we have the weaker player's epsilon. Okay, my computer just went to sleep. Thanks. But what we see here is that when an epsilon 1 player is playing an epsilon 9 player, the stronger player is only winning like 44% of the time, which isn't great. So we want to dig into why this is happening. And so what's great about simulation is we now have access to the distribution of throws to checkout, which we couldn't get straight from our MDP. So let's look at these distributions. So these are frequency histograms of the number of turns to checkout. And we've got a stronger player with epsilon 1 in red and a weaker player with epsilon 8 in purple. And what we see is that the variance, mean, and skew increase as your execution error increases. And what is a head start? What can a head start do? All it can really do is shift the distribution of the weaker player left and right, which is what we see. The heuristic head start shifts it, but because of that really long tail, for the weaker player, the stronger player is still at an advantage. And when we try to use our optimized version, we're overcompensating and we're giving the weaker player an advantage. So clearly, we need to do some more work here, and this is where dynamic credits come in. So we went back and we resolved the game, giving each player different numbers of credits, and then we saw what happened. So this is similar to the graph we were looking at before. This is the total expected turns starting from a score of 501. And on the x-axis here, we have the number of credits that a player was given. Wow, technology today. OK. And so what we find here, a few things. The main benefit comes from that first credit. So we can see that the slope of the line from 0 to 1 is much more pronounced than the rest of the credits. And this is because that first credit allows that real difficulty at the end of the game to be mitigated. It allows players with low execution error to hit that double and makes a big difference in the amount of time to check out. We also can calculate the dynamic credit handicap that would balance competition in the same way as before. So we have that line, a pro takes just below 6 turns to check out, and then we can find the appropriate handicap for each weaker player. So let's say for epsilon 9 in pink, they'll have about 6 credits, and that will allow them to check out in the same rough amount of time. And when we plug this back into our simulation model, we find something really interesting. Dynamic credits do a much better job balancing competition. It's not perfect, but we're much closer to 50-50. Let's look into why this is happening. So we have our distributions, and when we plot the same thing for dynamic credits, we see that the distribution has actually been reshaped. And this is because that long tail caused by the difficulty of checking out, we think, has been reduced. And indeed, we see that players usually save their credits to the end of the game. And what's really cool about this is we're sort of using a heuristic when we talk about competitive balance because we're just aligning the means of 2 distributions. But if the distributions are the same, then that also equalizes win probability. And we're trying to find kind of a theoretical explanation for this, but it's sort of intuitive in practice, and it's really nice because it allows this simplified framework to work. And it's a pretty cool result. OK, so yeah, we've sort of referred to this, but we've defined competitive balance as when 2 players have an equal expected number of throws or turns to check out. But we know that this is not fairness. Real fairness is when 2 players have equal win probabilities. But what's really nice about competitive balance is we can estimate it by solving a bunch of one-player models, which have about 2 million states, but you can solve a single MDP. It takes less, like around a minute. You can do it on a normal computer. You could plug it into an app that people could use at the pub. It's really, really practical. In order to model true fairness, you actually need a 2-player model. You have to consider both players at once. And this has around 2 billion states. And in order to consider optimal play with your opponent, you actually kind of need to plug it into a system of MDPs and it's just really impractical to solve. So what's really cool about dynamic credits is it allows us to use this simplified framework to achieve sort of the same result. So, in conclusion, existing Head Start handicap approaches are not fair. The imbalance in darts comes at the end of the game, and Head Starts can't really address this. Heuristic Head Starts that are used in practice leave the weaker player at a disadvantage, but trying to use our framework to optimize a Head Start leaves the stronger player at a disadvantage. And finding a truly fair Head Start is theoretically possible using that two-player model, but it's computationally impractical. And what's more is, like we mentioned at the beginning, it's still possible that no fair Head Start exists. So that we were looking at it with competitive balance, but even with fairness, there's a possibility that the stronger player just completely dominates the weaker player. So dynamic credits are a really promising alternative in this space. We're guaranteed, we can theoretically show that we're always guaranteed to have a value that can balance competition. It alters the distribution of the weaker player, so it mimics that of the stronger player. And because of this, we can accurately estimate it with a much simpler modeling framework. So that's all I have for today. Thank you so much for listening, and I would love to take questions. Thank you.
That was great. All right, we have time for a couple questions. You gotcha. All right, here we go.
Brendan Cooley, Big League Advantage. So you just alluded to it at the end, but the equilibrium of the game in which the players are trying to optimize win probability instead of minimizing the number of turns that they take is subtly different, but computationally a lot harder. So can you, I guess, talk a little bit about those constraints and why you guys chose to focus on the decision problem instead of the game theoretic problem, and how those strategic considerations would impact play if you actually took them, or if you actually tried to model them?
Okay, good question. So there's a paper that I mentioned at the beginning called Play Like the Pros by Hao and Wang, and they actually tried to look at the game theoretic approach of two players, and they found that considering your opponent in darts only really improves win probability by a couple of %. So they found in darts, because it's even more individual than baseball in a way, because you're sort of playing two independent games, and I guess there is some strategy in reacting to your opponent, but it's pretty minimal. So we thought that the single player estimation would probably be a good place to start. It's also just a lot simpler to compute. And yeah, so I guess the biggest point is that the game theoretic approach optimizing for it doesn't create that much value. It's a lot easier to evaluate it, actually, which we've done to kind of validate our approach as well. But I think it's just generally it takes a day, and you can't run it on a normal computer, so who is ever going to use this in practice? Whereas our approach has a much better chance of being used by average people when they're playing in a tournament. Does that answer your question?
Yeah, no, great.
Okay, thanks.
Thank you. Thanks, Rachel. Great presentation. I'm interested in your distribution of the really strong darts players versus the weak players and the size of those radiuses. Mm-hmm. What was your kind of decision as to how big to make those and what the size difference between the strong players and the weaker players were?
That's a great question. So I know, when you see the distributions, you might think, your weaker player is still pretty good. When I play darts, I'm just trying to hit the board. So that's a good question. So we did kind of look at some other players with, Epsilon 100 probably might still be better than me. But yeah, we did look at some different players. And you can see that like at epsilon 100, you're just aiming for the middle every time because you just don't want to miss. I think we chose 1 to 9 just because it was easiest to see the trends, because the scale for an epsilon 50 or 100 player is just totally different, and it's hard to have to identify the same patterns, I guess. So 1 to 9 was just clean for the purposes of our analysis. I would love to actually resolve for some of these players because I think it's more practical.
Yeah, I also wonder if there's maybe, it's not always like a circular distribution, right? That weaker players sometimes miss a lot more this way versus this way.
Yeah, you're so right. We chose like a nice, clean, symmetric. Actually, not when they're aiming for the middle, we chose symmetric, but yeah, you're right. Players will have different angles, kind of like the diagram I showed. So there's a whole extension of how to estimate the shape. It's just that that's like a whole other
For sure.
problem to solve. Yeah, good question.
Thanks.
Great. Well, let's thank Rachel. Great talk.
Thank you so much.